Hello, my name is Robert D. Hilster, and today I'm going to present a concept about how a circuit can find the right current. For general information, I am an electrical engineer. I graduated from the University of Michigan in 1960 with a BS degree in engineering physics and spent 42 years designing electronic circuits for telecommunications, specifically electronic switching systems. I retired in 2001 and spent most of my time studying gravity, but in 2015 I discovered a new concept for light which got my son's attention. That started a discussion of science between David and me that lasted for years. And hopefully there'll be a different slide presentation about the concept for light. So first of all, we look at Kirchhoff's voltage law, which assumes that current is constant. And his law states that the algebraic sum of all voltages around any closed loop in a circuit is zero, reflecting the conservation of energy. So in the circuit below, you have a battery with a 9 volts, and you got a 1 amp current caused by the 9 ohm resistances, and so you get 9 volts across the battery, 8 volts across the 8 ohm resistor, and 1 volt across the 1 ohm. You have battery gain, resistors lose, and you have a balanced circuit. And you can calculate the current pretty easily. Using Ohm's law, you just take the battery voltage and divide it by the sum of the two resistances. That's easy enough for us to do, and we've done it many times. But the question is, how does the circuit find the right current? For a simple battery resistor circuit, the circuit always finds the right current. It's not random chance. It is repeatable. No matter what value of the component R, it is a deterministic process. So what is this process that gets you the right current? The particle model, a model that my son David and I have developed, has an answer. And if you have a different answer or solution, let me know. Send me an email at my address, robert@thehilster.com. Using the particle model, we have some assumptions. The first and second assumption are related. The electron has no negative charge. The proton has no positive charge. Part of the reason for that is that there's never been a very good explanation of what makes an electron negative as to being positive or neutral, or what the same thing with a proton. And so charge is basically not part of this presentation. Interaction between particles then and atoms and molecules are strictly mechanical and gravitational. And we actually have two gravities, and we'll go into that a bit later. But gravity 1, G1, is Newtonian gravity, which we all know and feel every day. And G2 gravity is what holds the atom and molecule together. It really replaces what people have called the nuclear strong force. But there's no real definition of what that strong force is. And so in the presentation today, we hope to get a little more clarity by explaining what G2 gravity is. Okay, part of the theory of TPM theory is that it can lose G1. G1 is like an electron without a charge. And normally when you do circuit analysis, electrons don't leave the circuit. Everything stays well confined in the circuit, going around and around, doing their thing, and they don't escape. Uh, Here's a diagram. Let's say it's a resistor. We have the number of G1s entering is A. The number of ones that leave is the small b. And the ones, I should say escape is small b. The ones that leave the resistor is C. B is the number lost. And this is a new idea that most circuit engineers didn't have any considered or didn't need to. But leaving a conductor, electrons can leave a conductor. Einstein's photoelectric effect has got the Nobel Prize in 1921 for this, demonstrated that electrons can leave a conductor when the stimulating force is strong enough, whatever that is needs to be. So the TPM theory proposes that the electron can be lost by a simple mechanical collision. Hence, the current is not constant. In other words, you lose G1s, you lose electrons, it looks like you're going to lose current, although the loss of one electron in a 1 amp stream of electrons is, you're not even going to see it. But so you can have losses and not even know about it. What is needed here is a circuit diagram that shows the flow of G1s through the circuit and the gain and loss of G1 particles. Okay, so we're going to use the same circuit here as shown before, and I'm going to identify a new term called VG1, which assigns 0.1 volt to each G1. And the gain and loss around a circuit could be, and these are nominal values that match the components. A 9-volt battery emits 90 G1s in a unit of time, and the 8 ohms loses 80 in that same unit of time, and the 1 ohm loses 10 in that same unit of time. And so if you start with A equals 0, you add 90, then from the battery, the 8 ohm loses 80, and you're down to 10, and then the 1 ohm loses 10, and you're back to 0, and you have we have stabilized it. I had a temporary interruption there. So we'll get set up properly here and move right along. So we just explained how you gain and lose G1s as you go around this circuit. And the sum of G1s gained and loss equals 0. The circuit is stable when the addition of G1s by the battery equals the loss of G1s by the resistors. Simple addition of battery G1s and loss of G1s in resistors. But this is not the total. These to show how the circuit stabilizes, only the number of G1s added or lost are required. We're not talking about the total number. The total number of G1s flowing can be much higher. To understand how many could be flowing, consider this definition for 1 amp of current, where we define 1 amp of current as being approximately equal to 6.242 times 10 to the 18th electrons per second. So you can have a whole bunch of electrons or G1s flowing through the circuit, and the battery adds a few, resistors take out a few, and gets back to where it started. So it's not the total. We're only doing what is being added or lost. Okay, so here are some equations. The equations on the left are like Kirchhoff's equations, where the sum of the voltages equals 0. That's Kirchhoff using the voltage, and again, he assumes current is constant. The circuit on the equations on the right are equations in the form of G1s, of electrons. For example, B, which is the output of the battery, is equal to the input plus the added number of G1s by the battery. VB over VG1 will tell you how many G1s the battery adds. So you start with A as 0, then you get what the battery adds. Then to get C, you take B. B is the input to the R3 resistor, and it loses a certain percentage by going through R3. IFR is a new term, just like VG1 is. IFR is a term that tells us how many G1s are lost based on how many are input and what the resistor value is times this the IFR term. So we got both electrical equations and TPM equations. Now I'm going to do spreadsheets based on TPM equations. The following spreadsheets show that no matter the starting value of G1s, the result is the same. The value of VG1 is the volts assigned to each G1. Since this value is not known, it is set to 0.1 volts per G1. It's by arbitrary assignment, probably not even close to real, but that's the one I chose to use. The value of IFR, the interaction factor of a resistor, is not known, and it is set to 0.0001% per ohm. And you'll notice that when we look at the spreadsheets, that the charts all end in 56.103896, X being different in the two. So here's the first chart, and I start with A having 100 G1s being emitted at A, and I use the equations, the TPM equations, to calculate 20 cycles. And after 20 cycles, you can see there at the bottom in red is 56.1038963. Here I started with 50, and instead of going down from 100 to 56, I start with 50, and it increases to the same number, 56.1038961. So it arrives at the same point, no matter if you push too many electrons in, it comes down to a lower level. If you push too few, it builds up to a higher level, and that comes from using the TPM equations. And here's a complete spread chart, but I've taken the resistor values out, and it shows you that if you start at 50, you end at the bottom with 56.1038961. A comment. Because the values of VG1 and IFR were selected by me, the specific numbers in the charts are not correct. But by assigning the values, the charts show how the circuit finds the final value and reaches a stable circuit. How to find the real values of VG1 and IFR has not been determined. Thought about it a lot, and I actually came up at one time with a product. I think I came up with a product where VG1 times RFR was actually a constant. I never could prove that in such a way that I could make that as an absolute statement. Okay, that's how a circuit finds the right current, and by using the G1, it finds it. Here's an interesting point. You have a circuit of a battery and 3 resistors. Each one of those components doesn't know the battery doesn't know whether it's got one resistor, two resistors, or no resistors. Resistors don't know what the battery is and what the other resistor, it doesn't even know. So face it, components in a circuit don't know anything. They're not, they don't have the ability to think that through. But the one term that does go through all components is the current. The current gets to know what is happening in all the components, even though the components themselves are isolated. It's just a side point. Let's talk about the second gravity. I was working on refraction when I drew these pictures, the one on the left, and I asked what forces needed to cause the refraction at the top of the prism. I said, well, maybe a force like that blue arrow pointing down, right at the point where the red light hits the prism. And then I said, well, wait a minute, it also refracts down below, so I had to draw a force down below, and in reality, you have to draw a force all around the prism, because no matter where the light comes in, it refracts, except in the horizontal or vertical. So we're proposing that there's a second gravity here. The forces around the prism look very similar to the Newtonian forces around the Earth. We decided to call Newtonian gravity G1, and refraction gravity is G2. Now here's a couple of applications where G2 gravity comes into play. A copper-nickel battery generates a G2 force that acts as an electromotive force. So now I'm going to tell you that what this is saying, that the G2 force, the basis is gravity. It's a gravitational force. Now, first of all, if you build a battery with copper at the top and copper at the bottom, what you get is an equal loss of G2s through both plates, and no net force arrives. So a copper-copper battery doesn't work, and a nickel-nickel battery doesn't work, but a copper-nickel does work because there's fewer 20 G1s in copper versus nickel. Nickel has one more per atom. So you're going to lose a certain number of G1s going through the copper, and I'm suggesting arbitrarily that you lose 10 G2s. And through nickel, just to pick a number, it's not necessarily obviously the right number, but you lose 20, you get 80, and therefore you have a net of 10 G2s from the copper plate to the nickel plate, and it is specifically that net force that pushes the electron out of the negative end of the battery. Okay, another application of the G2 force is it keeps the magnetic field around a magnet in orbit around and through it. Now, the G1 particle here is moving at speed c. The implication here is if you're going to control that specific path the way it's shown, it's very likely that the speed of the F2 particle, or G2 particle, and the speed of the F2 force is faster than light. Probably has to be faster than light. And specifically, I don't have a slide on it, but I think you have to have a force faster than light to create a rainbow. Obviously, G2 gravity as an atomic binding force, or what we call the nuclear strong force. Little red dots are electrons moving around at high speed, speed c. F2 force surrounding it, holding the thing together, the binding force must be faster than the electrons, or those electrons will move away very easily. Well, that's my presentation about the second gravity, and there's several applications. Hope you enjoyed the presentation as much as I enjoyed going through this with my son David, and a special thanks to him for setting up this video so I could make the presentation. Thank you and have a nice day.